Look up at the night sky, and you're gazing into an ocean of stars, each one a distant sun, some so colossal they defy comprehension. But among them lurk the true titans of the cosmos, stars so massive they could swallow our entire solar system without a second thought. Imagine a single star so vast that if placed at the center of our own solar system, its surface would stretch beyond the orbit of Jupiter. These aren't just stars, they're cosmic behemoths, blazing furnaces of unimaginable power, and their existence challenges everything we think we know about the universe. What if I told you that some of these stars are so luminous, a single second of their energy output could power human civilization for thousands of years? Or that their deaths, cataclysmic explosions known as supernova, scatter the very elements that make up our bodies across the galaxy. These aren't just abstract facts, they're the threads connecting us to the vast, unfolding story of the cosmos. And today, we're diving deep into the heart of that mystery, uncovering 30 astonishing truths about the universe's most massive stars, facts so incredible, they'll leave you questioning the very fabric of reality. From stars that spin so fast they tear themselves apart to others so dense they warp space-time itself, this journey will take you to the edge of what's possible. You'll discover how these giants shape the galaxies around them, forging the building blocks of life in their fiery cores, and by the end, you'll never look at the night sky the same way again. So buckle up, because we're about to explore the extremes of stellar existence, where the laws of physics bend and the universe reveals its most dazzling secrets. UY Scuti isn't just a star, it's a cosmic colossus that redefines the word giant. Picture our sun, a blazing sphere so vast that 1,000,000 Earths could fit inside it. Now imagine a star so much larger that it makes the sun look like a speck of dust. That's UY Scuti, a hypergiant with a radius roughly 1,700 times wider than our sun's. If you placed this monstrous star at the center of our solar system, its searing surface would stretch beyond the orbit of Jupiter, swallowing Mercury, Venus, Earth, Mars, and the asteroid belt without a second thought. Even Saturn, with its iconic rings, would orbit deep within this star's fiery atmosphere. But size isn't the only thing that makes UY Scuti mind-bending. Found in the constellation Scutum, this star is a pulsating variable, meaning it rhythmically swells and shrinks over time. Think of it like a cosmic heartbeat, except each pulse could take years, and the energy released would dwarf anything our sun could produce in 1,000,000 lifetimes. Despite its unimaginable scale, UY Scuti isn't particularly dense. In fact, if you could somehow scoop up a chunk of it, the material would be millions of times less dense than Earth's atmosphere, more like a glowing fog than the solid furnace we imagine. What's even stranger, UY Scuti won't last forever. Stars this massive live fast and die young, burning through their fuel in just a few million years before meeting a spectacular end. When that happens, it won't just fade away, it'll explode in one of the most violent events in the universe, a supernova so powerful it could outshine entire galaxies. For now, though, UY Scuti stands as a testament to the universe's ability to create wonders beyond our wildest dreams, a reminder that even in the vastness of space, there are still giants waiting to be discovered. Stars like UY Scuti belong to an exclusive club of cosmic anomalies, the Hypergiants. These aren't just oversized stars, they're unstable, tempestuous monsters battling against their own enormity. While our sun will burn steadily for 10 billion years, Hypergiants blaze through their fuel in just a few million, living lives of extravagant extremes before meeting spectacular ends. What makes them so volatile? It all comes down to mass, too much of it. A hypergiant's core burns at unimaginable temperatures, fusing elements at a rate so furious that the star can't hold itself together. Imagine trying to contain a bonfire with tissue paper. That's the struggle these stars face. Their outer layers, heated to millions of degrees, are constantly blasted into space by the sheer force of radiation pushing outward. This relentless mass loss creates vast, glowing halos of ejected material, like a cosmic hourglass counting down to the star's inevitable collapse. Even their shapes betray their instability. Unlike the Sun's neat, spherical form, hypergiants often appear distorted, with patches of their surface boiling away into space. Some spin so fast they flatten into squashed ovals, while others pulsate violently, expanding and contracting like a dying breath. And here's the cruel irony: the more massive a star is, the shorter its life becomes. While smaller stars like our Sun age gracefully, hypergiants are the rock stars of the cosmos, burning bright, burning fast, and leaving behind legends written in supernova. Yet their fleeting existence is what makes them so important. In their brief, fiery lives, they forge heavy elements like iron, gold, and uranium in their cores, elements that will one day become part of planets, plants, and even people. Every time you hold a piece of metal, you're holding stardust crafted in the heart of a giant. So while hypergiants may be rare and short-lived, their legacy is written across the universe and in the very fabric of our bodies. Stephenson 218 doesn't just shine, it obliterates every notion of stellar brightness we've ever had. This crimson behemoth radiates with the intensity of 440,000 suns, a luminosity so staggering it defies earthly comparison. If you swapped our Sun for Stephenson 218, the sheer glow would vaporize every planet out to Neptune in an instant. Earth wouldn't just be bathed in light, it would be incinerated, reduced to ash in the face of a star that outshines our entire solar system like a supernova next to a candle. What makes this red supergiant so radiant? Its secret lies in its size and temperature. Though cooler than our Sun at around 3,000 degrees Celsius, Stephenson 218's colossal surface area, stretching over 2,000 times wider than the Sun, allows it to emit energy at an incomprehensible rate. Picture billions of nuclear reactions erupting across every square kilometer of its turbulent surface, each one contributing to a light show that could illuminate entire galaxies. And here's the twist: we're seeing Stephenson 218 as it was 19,000 years ago. Nestled within the distant Stephenson 2 star cluster, its light has traveled across millennia just to reach our telescopes. By now, this star might already have met its fate, collapsing in on itself or exploding in a supernova that would have been visible from Earth even in broad daylight. Yet for now, it stands as a flickering monument to the universe's ability to create monster stars so luminous they challenge our very understanding of cosmic limits. Every photon it emits carries a whisper from the edge of possibility, reminding us that even in the darkness of space, there are giants blazing trails we've only begun to trace. Even the universe has its limits, or at least it's supposed to. Meet the Eddington Limit, a cosmic rulebook that says stars shouldn't grow beyond 150 to 200 times the mass of our Sun. Think of it like a speed limit for stellar growth. Once a star hits this threshold, the radiation bursting from its core becomes so intense that it starts pushing against the star's own gravity. At this point, the outward force of light literally fights the inward pull of gravity, creating a precarious balance. If the star gets any heavier, the radiation wins, blasting its outer layers into space like a cosmic sandblaster. But here's the catch: some stars laugh in the face of this limit. Take R13601, for example, a leviathan tipping the scales at over 250 solar masses. How does it defy the rules? The answer lies in chaos. Stars like this aren't just burning hydrogen in a tidy core. They're turbulent, messy factories where pockets of extreme heat and density create uneven radiation pressure. Imagine trying to balance a beach ball on a geyser. Some parts erupt violently while others barely hold on. These stars cheat the Eddington Limit by being imperfect, their instability allowing them to cram in more mass before radiation tears them apart. And then there's the role of composition. Stars born in the early universe were made of almost pure hydrogen and helium, lacking heavier elements that help radiate energy away. This simplicity let them grow far larger than modern stars without immediately hitting the Eddington wall. It's like comparing a bonfire in open air to one trapped in a metal box. The latter overheats faster. Yet even these rule breakers can't escape forever. Eventually, gravity and radiation reach a breaking point, and the star either sheds colossal amounts of material or meets a cataclysmic end. So while the Eddington Limit sets the universe's speed limit for stardom, the most massive stars remind us that nature always finds a way to bend, if not outright break, the rules. R13601 isn't just massive, it's a cosmic anomaly that rewrites the rules of stellar existence. Tucked inside the Tarantula Nebula, a swirling stellar nursery 170,000 light-years away, this star tips the scales at a staggering 315 times the mass of our Sun. To put that into perspective, if you gathered every planet, moon, and asteroid in our solar system and crushed them together, you'd still need 30 more copies of Jupiter just to match the weight of this single star. It's so colossal that its very existence defies what astronomers once thought possible for stellar formation. The birth of a star like R13601 is a violent, chaotic event. Most stars form from collapsing clouds of gas, but to reach this mind-bending size, R13601 likely grew through a series of cosmic mergers, smaller stars smashing together like celestial bumper cars until they created this unstoppable behemoth. Some theories even suggest it swallowed siblings in its own stellar cluster, gorging itself on their mass until it became the heavyweight champion of the known universe. But here's the catch: stars this massive shouldn't technically exist. Traditional models predict that radiation pressure from a newborn star's core should blow away surrounding gas before it can grow beyond 150 solar masses. Yet R13601 laughs in the face of physics, forcing scientists to rethink how the most extreme stars are born, and its sheer power is just as terrifying as its size. The solar winds blasting from R13601 move at over 5 million kilometers per hour, fast enough to circle Earth twice in the time it takes to boil a pot of water. These aren't gentle breezes, they're apocalyptic particle storms, stripping away the star's own outer layers at a rate of 1 Earth mass every 3 weeks. Imagine a hurricane made of plasma, so fierce it could evaporate entire planets in seconds. Yet for all its ferocity, R13601 is living on borrowed time. Stars this massive burn through their fuel in just a few million years, a cosmic blink compared to our Sun's 10 billion-year lifespan. When it finally dies, it won't just fade away. It'll detonate in a hypernova, an explosion so powerful it could outshine its entire host galaxy and leave behind a black hole with an appetite for the impossible. For now, though, R13601 stands as a blazing monument to the universe's most extreme laboratories, a place where the rules are written in fire and rewritten by giants. Wolf-Rayet stars don't merely burn, they rage. These stellar monsters, named after the astronomers who first documented their bizarre spectra, are the universe's ultimate rebels, cloaked in tempests of their own making. Unlike the steady glow of ordinary stars, Wolf-Rayet stars blast their outer layers into space at speeds exceeding 2,000 kilometers per second, fast enough to cross the continental United States in under 2 seconds. These aren't gentle breezes, they're supersonic hurricanes of plasma, tearing through the cosmos with enough force to sculpt entire nebulas from their own disintegrating bodies. Hubble's iconic images reveal their fury in breathtaking detail. Surrounding these stars are vast, intricate shrouds of gas and dust-ejected material glowing in neon hues of blue and gold. Picture a star literally unraveling before your eyes, its atmosphere peeling away like the layers of an onion caught in a tornado. The most striking of these, the Crescent Nebula, looks less like a star and more like a celestial fireworks display frozen mid-explosion. But what makes Wolf-Rayet stars truly extraordinary isn't just their violence, it's what they're made of. Strip away their outer chaos, and you'll find cores rich in heavy elements like carbon, nitrogen, and oxygen, forged in the star's nuclear furnace and hurled into space by those relentless winds. This isn't just stellar death throes, it's cosmic recycling on a grand scale. Every atom blasted into the void becomes raw material for future stars, planets, and perhaps even life. And here's the twist: Wolf-Rayet stars are essentially naked stellar cores. Most stars hide their fused elements deep within, but these giants flaunt them, their outer hydrogen layers long since blown away to expose the exotic chemistry beneath. It's as if the universe took a scalpel to a star, dissecting it alive to reveal the secrets at its heart. Yet their brilliance is fleeting. Wolf-Rayet stars live fast, die young, and leave behind some of the most spectacular corpses in the cosmos. Within a few 100,000 years, a blink in cosmic time, they'll detonate as supernova or even hypernova, scattering their heavy element treasure across the galaxy. For now, they serve as both destroyers and creators, their fury shaping the very fabric of the universe one atomic storm at a time. There's a catastrophic fate awaiting the universe's most massive stars, one so violent it leaves nothing behind. This phenomenon, called pair instability, targets stars weighing more than 130 times our Sun's mass. Unlike typical supernova, which leave behind neutron stars or black holes, these explosions are so thorough they erase themselves from existence entirely. The process begins deep in the star's core, where temperatures soar beyond 1 billion degrees hot enough for photons, the very particles of light, to transform into matter. Normally, photons stream outward, helping stars maintain their balance. But in these extreme conditions, they spontaneously convert into electron-positron pairs, particles that provide no outward pressure. The core's support system vanishes in an instant, like yanking the foundation from a skyscraper. Gravity seizes its chance, collapsing the star inward with unimaginable force. What happens next defies the laws of ordinary stellar death. As the core implodes, temperatures spike even higher, reigniting nuclear fusion in a runaway chain reaction. The entire star detonates, not just its outer layers. Every atom, from core to surface, is engulfed in a fireball so powerful it outshines entire galaxies. These explosions, called pair instability supernova, release so much energy that they vaporize the star down to its last particle. No black hole, no neutron star. Just an expanding cloud of stardust and a flash of light that echoes across the cosmos for millions of years. Astronomers suspect they've glimpsed these events before. In 2007, a supernova named SN 2006 Gi flickered to life halfway across the universe, shining with the brightness of 50 billion suns, a clue that something extraordinary had occurred. The light curve, a graph tracking its brightness over time, matched predictions for pair instability explosions, lingering far longer than typical supernova. Another candidate, SN 2022 JLS, erupted with such violence that its shockwaves heated surrounding gas to millions of degrees, creating an afterglow visible for months. Each of these events could be the cosmic signature of a star so massive it literally blew itself apart from the inside out. What's truly unsettling is that pair instability supernova might be far more common in the early universe, where gargantuan stars thrived in the pristine hydrogen-rich environment. Some theories suggest these explosions seeded the cosmos with its first heavy elements, scattering the raw materials for planets and life long before our sun even ignited. Today, spotting one is like catching a glimpse of a cosmic ghost, a fleeting reminder that even the mightiest stars can vanish without a trace. Why Canis Majoris doesn't just occupy space, it dominates it. This crimson hypergiant, one of the largest known stars in the Milky Way, is so vast that its outer atmosphere could swallow Saturn if placed at the center of our solar system. Its radius stretches over 1,400 times wider than the Sun's, making it not just a star but a cosmic titan whose very presence bends the rules of physics. But what's truly mesmerizing isn't just its size, it's the chaos unfolding on its surface. Unlike the steady glow of smaller stars, UY Canis Majoris is a seething, unstable furnace, its outer layers pulsating like a slow-motion heartbeat. Every few decades it convulses, ejecting colossal clouds of dust and gas into space, enough material to form entire planets. Hubble's images reveal the aftermath of these outbursts, intricate, nebula-like structures swirling around the star, illuminated by its fiery light. These aren't delicate veils of gas, they're the scars of celestial violence, remnants of a star tearing itself apart. Some of these ejectors span billions of kilometers, forming filaments and knots that drift through space like smoke from an endless explosion. And the dust isn't just ordinary stardust, it's rich in molecules like titanium oxide and silicon carbide, ingredients for future worlds. Yet this spectacle is a prelude to something far more dramatic. UY Canis Majoris is living on borrowed time. Hypergiants this massive rarely survive more than a few million years, and all signs point to an impending supernova, one that could outshine the moon in our night sky when it finally detonates. When that happens, the star won't just fade away. It'll unleash a shockwave powerful enough to sterilize nearby star systems, scattering its heavy elements across the galaxy. For now, though, it stands as a beacon of stellar extremity, a reminder that even in the quiet of space, some stars refuse to go gently. In the beginning, the universe cooked up stars unlike anything we see today. Monstrous, metal-free giants that defied every rule of modern stellar physics. These firstborn stars, known as population 3 stars, formed from nothing but pristine hydrogen and helium, the elemental leftovers of the Big Bang. Without heavier elements to help radiate heat away, their cores burned hotter and collapsed more violently, allowing them to balloon to sizes we can barely comprehend. Some may have reached 1,000 times the mass of our sun behemoths, so vast their gravitational pull could bend light into knots. Fast forward to today, and the universe has changed its recipe. Every star born now carries traces of heavier elements: carbon, oxygen, iron, forged in the hearts of those early giants and scattered by their explosive deaths. This metallicity, as astronomers call it, acts like a cosmic braking system for stellar growth. Metals in a star's composition help cool collapsing gas clouds, allowing radiation to escape more efficiently. The result: modern stars rarely grow beyond 100 solar masses, their potential size capped by the very debris of their ancestors. The difference is staggering. Picture a wildfire in an open field versus one trapped in a metal barrel. The first rages unchecked, while the second burns hotter but contained. Population 3 stars were those unchecked infernos, while today's metal-rich giants like Eta Carinii burn fiercely but within tighter limits. Even so, metallicity isn't just a constraint, it's a catalyst for diversity. Heavy elements enable complex molecules to form in stellar nurseries, leading to everything from rocky planets to the chemistry of life. Yet traces of those primordial monsters might still linger. In 2015, astronomers discovered a star named SMSSJ 0313-670843, a relic so metal poor it's nearly a time capsule from the early universe. Its composition suggests it formed from the remains of a single population 3 stars supernova, a ghostly fingerprint of the cosmos's first giants. So while we'll never see those original behemoths directly, their legacy lives on in the atoms they forged, the laws they tested, and the cosmic puzzle they left for us to solve. Imagine 2 stars locked in a gravitational dance so intense they spiral closer until catastrophe. Their surfaces touch, their cores ignite, and in a flash of cosmic violence they become one. This isn't science fiction, it's how some of the universe's most massive stars might be born. binary star mergers could explain the existence of hypergiants so colossal they defy conventional formation theories. Take Eta Carinae, a star system that's essentially a ticking time bomb, with two stars orbiting each other, one weighing 90 times the Sun's mass, the other 30. Their gravitational tug of war has already triggered eruptions powerful enough to form the Homunculus Nebula, a glowing hourglass of ejected material spanning trillions of kilometers. Astronomers suspect these stars are doomed to collide within the next 100,000 years, a blink in cosmic terms. When they do, their merger could create a single star surpassing 200 solar masses, a monster that would instantly vault into the top tier of stellar heavyweights. But how does this process work? Picture two fireballs circling each other at dizzying speeds, their outer atmospheres mingling like smoke from dueling wildfires. As they spiral inward, tidal forces stretch and distort their shapes, stripping away gas until their cores finally slam together. The resulting energy release would outshine a supernova, forging a hypergiant with a turbulent internal structure unlike anything born from a single collapsing gas cloud. Eta Carinae isn't the only candidate. In the Small Magellanic Cloud, a star named R144 displays bizarre outbursts that hint at a hidden companion, possibly another massive star being slowly consumed. Over millennia, such systems may quietly produce hypermassive stars through gradual mergers, their growth hidden behind veils of dust until they erupt onto the cosmic stage. Even more intriguing, some theorists suggest the first stars in the universe, those elusive population, three giants, might have formed this way, their rapid mergers leaving no trace beyond the heavy elements they forged. Yet these events aren't clean cosmic handshakes. Mergers eject staggering amounts of material, littering space with debris that glows for centuries. They also spin the newborn star at breakneck speeds, potentially triggering further eruptions as centrifugal forces battle gravity. The result is a star that doesn't just burn, it rages, its entire existence a testament to the chaos that birthed it. And when these merged giants finally die, their supernova could be unlike anything we've seen, enriched by the unique chemistry of their turbulent origins. So while solitary stars dominate our night sky, it's the secret dances, the collisions and consummations that may have built the universe's true titans. Rho Cassiopeiae isn't your typical massive star, it's a cosmic chameleon caught between identities. Classified as a yellow hypergiant, this rare stellar breed glows with a golden hue, cooler than blue supergiants, yet infinitely more volatile than ordinary stars. Imagine a celestial pressure cooker on the verge of bursting. That's Rho Cassiopeiae, a star so unstable it periodically hurls entire suns worth of material into space without warning. What makes yellow hypergiants like Rho Cassiopeiae so special? They occupy a precarious middle ground in stellar evolution, too massive to age gracefully but not quite ready to collapse. Most stars this size would burn as blue supergiants, their surfaces scorching at over 20,000 degrees Celsius. But Rho Cassiopeiae's outer layers hover around 7,000 degrees, just cool enough for exotic molecules like titanium oxide to form in its atmosphere, giving it that distinctive golden glow. Then there are the eruptions. In 2001, astronomers witnessed Rho Cassiopeiae rip itself apart in a colossal outburst, ejecting 10,000 Earth masses of material in mere months. The event dimmed the star's light by an entire magnitude, visible even to backyard telescopes. This wasn't just a stellar flare. It was a full-scale atmospheric rebellion as the star's outer layers overheated and blasted into space at over 4 million kilometers per hour. But why such violence? Yellow hypergiants are caught in a tug of war between expansion and contraction. Their cores fuse elements at a breakneck pace, forcing the star to swell into a supergiant. Yet radiation pressure keeps peeling away their outer layers, preventing them from growing too large. The result is a star in constant flux, oscillating between states like a candle flame guttering in the wind. For Rho Cassiopeiae, this balancing act can't last. Within the next 50,000 years, possibly tomorrow by cosmic standards, it will either shed enough mass to become a blue variable star or continue expanding into a red hypergiant. Either path leads to catastrophe, a supernova capable of briefly outshining its entire host galaxy. Until then, it remains one of the rarest sights in the cosmos, a dying giant painting the void with gold, its every convulsion rewriting the rules of stellar life and death. Luminous blue variables are the divas of the cosmos, volatile, unpredictable, and prone to spectacular tantrums that rewrite the rules of stellar behavior. Take P Cygni, a star so temperamental that its 17th century outburst left astronomers scratching their heads for decades. One moment it shone brightly in the constellation Cygnus, the next it mysteriously dimmed before flaring up again like a celestial strobe light. Modern observations reveal why. LBVs are caught in a perpetual tug of war between radiation and gravity. Their surfaces so unstable they periodically detonate entire layers into space without warning. These explosions aren't subtle. When an LBV like Eta Carinii erupts, it doesn't just shed material, it hurls out enough gas and dust to form multiple solar systems in a single event. The Homunculus Nebula, a bipolar cloud stretching trillions of kilometers, stands as fossil evidence of Eta Carinii's 19th century outburst, which briefly made it the second brightest star in Earth's night sky. Time-lapse images show these nebulae expanding at speeds exceeding 7 million kilometers per hour, their intricate structures unfolding like cosmic origami. What drives this chaos? LBVs occupy a precarious sweet spot in stellar evolution, too massive to stabilize, yet not quite ready to collapse. Their cores generate such intense radiation pressure that the star's outer layers essentially float on a bubbling sea of energy. Occasionally, this balance tips and the star puffs up like a balloon until gravity can no longer hold it together. The result, a cataclysmic eruption that can eject 20 times the Sun's mass in a single go. But the real surprise is how these outbursts sculpt their surroundings. Hubble images of LBVs like Eta Carinii reveal delicate, lace-like nebulae complex webs of gas ionized by the star's ultraviolet fury. These aren't just debris fields, they're evolving ecosystems where shockwaves trigger new rounds of star formation, proving even stellar tantrums can have creative consequences. And then there's the ultimate irony. LBVs might be cosmic imposters. Many astronomers suspect these variables aren't a true phase of stellar life, but rather a brief, violent tantrum some stars throw as they transition from blue supergiants to Wolf-Rayet stars. It's as if the universe decided even giants need a midlife crisis, one that involves hurling chunks of themselves across the galaxy. What's certain is that LBVs live on borrowed time. Their outbursts are the prelude to an even grander finale, a supernova or hypernova that will scatter their enriched guts across interstellar space. Until then, they remain the universe's most flamboyant performers, staging light shows so unpredictable they keep astronomers constantly watching the skies. Most stars, like our Sun, meet their end quietly collapsing into dense white dwarfs no larger than Earth. But there's a cosmic speed bump on this path, the Chandrasekhar limit, a fundamental rule stating that no white dwarf can exceed 1.4 times the Sun's mass without catastrophic consequences. Push past this limit, and the star's core can no longer resist gravity's crush, triggering either a thermonuclear explosion or an implosion into a black hole. This boundary isn't just theoretical, it's written in the ashes of countless dead stars scattered across the galaxy. Now, imagine a star so massive it laughs in the face of this limit from birth. For hypergiants and supermassive stars, the Chandrasekhar limit isn't an endgame, it's a starting point. These titans aren't bound by the same rules as smaller stars because their cores operate on an entirely different scale. While a white dwarf is held up by quantum mechanics, the repulsion of electrons packed shoulder to shoulder, a massive star's core is a roiling fusion factory, forging heavier elements until gravity overpowers all resistance. Here's where physics takes a dramatic turn. When a massive star's core accumulates enough iron, fusion abruptly stops. No energy is released, and in an instant, the core's outward pressure vanishes. Gravity wins, and the core collapses at nearly a quarter the speed of light. But unlike a white dwarf's genteel decay, this implosion has two possible outcomes, neither of them quiet. If the core's mass falls between 1.4 and roughly 3 solar masses, it rebounds as a supernova, leaving behind a neutron star so dense a teaspoon of it would weigh 1 billion tons. Cross 3 solar masses, though, and the collapse doesn't stop. The core punches straight through the Chandrasekhar limit, through neutron degeneracy, and into oblivion, forming a black hole with an event horizon from which not even light can escape. The irony, the Chandrasekhar limit still governs these cataclysms just from the shadows. It's the dividing line between orderly stellar retirement and cosmic pandemonium. For massive stars, death isn't about respecting limits, it's about obliterating them. And in doing so, they don't just fade away. They rewrite the rules of the universe, scattering the elements of life across the void or vanishing into the ultimate mystery of a singularity. When a typical massive star explodes as a supernova, it's one of the most violent events in the universe, but some stars take destruction to an entirely different level. Hypernova are the supernova's far more ferocious cousins, erupting from stars packing 30 or more times the sun's mass. The difference isn't just scale, it's annihilation. A regular supernova releases enough energy in seconds to outshine its entire galaxy, but a hypernova, multiply that by 100, add a focused jet of pure destruction, and you're just beginning to grasp its power. The secret lies in the collapsing core. In a standard supernova, the star's center implodes into a neutron star, a city-sized orb so dense it bends space-time. But hypernova progenitors are too massive for that elegant fate. When their cores collapse, gravity doesn't stop at neutron star density. It keeps crushing matter until even neutrons dissolve into an infinitely dense point, a black hole. What happens next is catastrophic. As matter spirals into the newborn singularity at near light speed, it doesn't go quietly. Some material gets funneled into twin jets erupting from the star's poles, piercing through the stellar corpse like cosmic blowtorches. These jets, hotter than 1 trillion suns, emit concentrated gamma radiation, the most energetic light in existence. That's how we detect hypernova across the universe, by their gamma-ray bursts. These flashes, lasting from milliseconds to minutes, carry more energy than the sun will produce in its entire 10 billion-year lifespan. If one occurred within a few thousand light-years of Earth, the radiation would sterilize our planet. Fortunately, hypernova are rare. We spot perhaps 1 per million years in a galaxy like ours. But when they do ignite, the aftermath is unmistakable. While a supernova leaves behind a neutron star or small black hole, hypernova forge black holes with masses rivaling entire star clusters, and the surrounding nebula glows for millennia, painted with elements forged in the explosion's hellish heart. Perhaps the most famous hypernova candidate, SN 1998BW, was tied to a gamma-ray burst so luminous it briefly outshone the rest of the observable universe combined. Telescopes later revealed its host galaxy lacked heavy elements, suggesting the progenitor star was a primordial giant, a relic from when the universe built its most monstrous stars. Today, hypernova continue to shape galaxies, seeding them with gold, platinum, and uranium, while their black hole remnants lurk in the darkness, waiting for their next meal. When a hypergiant star collapses, we usually think of two outcomes: either it leaves behind a neutron star or vanishes into a black hole. But some theorists suggest there's a third, far stranger possibility lurking in the wreckage: a quark star. This hypothetical remnant would push matter beyond the crushing density of a neutron star, breaking down even those resilient particles into something even more exotic, a soup of free-floating quarks, the fundamental building blocks of all matter. How does this happen? In a typical neutron star, gravity squeezes atomic nuclei so tightly that protons and electrons merge into neutrons, creating a city-sized orb of nearly pure neutronium. But if the dying star is massive enough, perhaps 20 or 30 times heavier than our Sun, that compression might not stop there. The neutron star's core could reach pressures so extreme that neutrons themselves shatter, their three constituent quarks, 2 down and 1 up, spilling out to form a bizarre new state of matter, quark-gluon plasma. This substance isn't just dense, it behaves like a perfect, frictionless liquid with quarks flowing freely instead of being locked inside particles. The implications are staggering. A quark star would be smaller and hotter than a neutron star of the same mass, its surface temperature soaring above 1 million degrees. Its crust, if it even has one, might consist of strange matter, a hypothetical material made of up, down, and strange quarks that's denser and more stable than anything in our known universe. Some theories even suggest strange matter could be contagious. If a chunk broke off and collided with normal matter, it might convert that too into strange matter, triggering a runaway reaction. But how would we spot one? Quark stars might disguise themselves as neutron stars at first glance, but subtle differences could betray their true nature. Their extreme density would make them spin slightly faster and cool more slowly than neutron stars. Some pulsars, like the famously fast-spinning object at the heart of the supernova remnant Cassiopeia A, exhibit properties that don't quite fit neutron star models. Could they be quark stars in hiding? There's also the mystery of certain supernovae that seem inexplicably bright. If the collapsing core briefly formed a quark star before becoming a black hole, the energy released might explain those anomalous explosions. Of course, quark stars remain purely theoretical. No telescope has definitively spotted one yet. But if they do exist, they'd represent a missing link between neutron stars and black holes, a place where matter stops obeying the rules we know and starts playing by quantum ones we barely understand. For now, they live in the realm of equations and simulations, ghostly reminders that even the most violent stellar deaths might still hold surprises we haven't dreamed of. Hidden in the constellation Sagittarius, just 25,000 light-years from Earth, burns one of the Milky Way's most radiant monsters, the Pistol Star. This blue hypergiant outshines our Sun by a factor of 10,000, a luminosity so intense it could illuminate planets orbiting stars halfway across the galaxy. Named for the pistol-shaped nebula it sculpted with its own violent outbursts, this star doesn't just burn, it hemorrhages energy at a rate that defies earthly comparison. Every second, it radiates more energy than our Sun will emit in an entire year, a ceaseless torrent of light that pushes the boundaries of stellar physics. But the Pistol Star's most astonishing feature isn't its glow, it's the sheer volume of itself it's hurling into space. Each year, this hypergiant sheds 10 Earth masses worth of material, ejecting gas at speeds exceeding 2 million kilometers per hour. To put that into perspective, in the time it takes you to watch this video, the Pistol Star has already blasted a mass equivalent to Mount Everest into the void. These aren't gentle solar winds, they're apocalyptic gales, stripping the star down to its core like a cosmic sandblaster. Hubble images reveal the aftermath, vast, intricate structures of ionized gas glowing in the nebula around it, a graveyard of the star's own flesh. What drives such extreme mass loss? The Pistol Star exists in a perpetual state of rebellion against its own gravity. Radiation pressure from its core is so fierce that it overpowers gravity's grip on the star's outer layers, flinging them outward in a continuous eruption. Imagine trying to hold water in your hands while standing under a waterfall. That's the battle this star wages every moment of its existence. Unlike smaller stars that shed mass gradually, hypergiants like this one experience violent, episodic outbursts. Roughly 4,000 years ago, the Pistol Star likely ejected an entire solar system's worth of material in just a few centuries, an event that carved the nebula we see today. And here's the twist: the pistol star is a ticking time bomb. Originally thought to weigh over 200 solar masses, its relentless shedding has slimmed it down to roughly half that, yet it's still too massive to die quietly. When its core finally collapses, the explosion could rival the most energetic supernova on record, a farewell fireworks show visible across the galaxy. For now, though, it stands as a blazing testament to the universe's capacity for extravagance, a star that doesn't just live loudly, but leaves pieces of itself strewn across the cosmos as a reminder of its passage. In the cosmic dance of stellar life cycles, massive stars don't just burn, they throb. Enter the instability strip, a narrow band on the Hertzsprung-Russell diagram where hypergiants and supergiants like Betelgeuse undergo wild, unpredictable pulsations. Picture a star breathing, its outer layers expanding and contracting like a colossal cosmic lung, sometimes swelling to twice its normal size before collapsing back in on itself. These aren't gentle rhythms, they're seismic convulsions that can eject entire planetary atmospheres worth of material into space in a single stellar heartbeat. Betelgeuse's dramatic dimming in 2019 offered a front-row seat to this phenomenon. For months, the red supergiant's light faded by nearly 2/3, sparking speculation it might be on the verge of explosion. Turns out it was just shedding a colossal cloud of dust, a byproduct of its pulsations that temporarily obscured its glow. But this event revealed something deeper. Stars in the instability strip don't just flicker, they hemorrhage mass in fits and starts, their surfaces boiling with turbulence that defies simple models. The physics behind these pulsations is as beautiful as it is violent. In smaller stars, energy flows steadily from core to surface, creating stable light output. But for massive stars, radiation gets trapped in their bloated outer layers, building pressure until it triggers explosive expansions. As the star swells, it cools just enough for ionized gas to recombine into atoms, becoming opaque and trapping even more heat, which forces another expansion. This feedback loop creates oscillations that can last years, each cycle stripping away more of the star's outer envelope. Here's where it gets tricky for astronomers. These violent mood swings drastically shorten stellar lifespans. Traditional models estimate a star's age by its mass and brightness, but pulsating hypergiants rewrite the rules. Every mass loss episode reduces their fuel reserves prematurely, like a car with a gas tank that springs leaks at random intervals. Betelgeuse, for instance, may die hundreds of thousands of years earlier than predicted because of its erratic shedding. Even more confounding, these outbursts seed space with heavy elements long before the star's final explosion, creating chemical footprints that linger for eons. The instability strip isn't just a curiosity, it's a cosmic demolition zone where the universe's largest stars literally shake themselves apart. And as telescopes catch more of these giants mid-convulsion, one thing becomes clear. In the lives of massive stars, stability is the exception, not the rule. Their deaths may be written in the laws of physics, but the path there is anything but orderly. Before the first stars ignited, the universe may have hosted something far stranger: dark stars, colossal behemoths powered not by nuclear fusion, but by the annihilation of dark matter. Picture a star thousands of times wider than our solar system, glowing faintly not with the fierce light of hydrogen burning, but with the eerie, sustained energy of particles colliding in the shadows. These hypothetical giants, if they existed, would rewrite the origin story of cosmic dawn. How could dark matter fuel a star? The theory hinges on weakly interacting massive particles, WIMP, a leading candidate for dark matter. If these particles occasionally collide and annihilate in the dense cores of primordial gas clouds, the resulting energy could heat the gas enough to prevent collapse into conventional stars. Instead of igniting fusion, the cloud would stabilize as a vast, cool sphere, radiating dimly for millions of years as it steadily consumed the dark matter trapped within. Simulations suggest these structures could balloon to 10 million times the mass of our Sun, dwarfing even the largest modern hypergiants. Their surfaces would hover at temperatures barely warm enough to melt ice, yet their sheer size would make them visible across the cosmos. The implications are staggering. Dark stars might have served as cosmic incubators, their gentle glow providing the universe's first light long before fusion-powered stars emerged. Some models even propose they could have seeded supermassive black holes, collapsing directly into these enigmatic objects when their dark matter fuel ran out. If remnants of these stars still drift through galactic halos today, their faint signatures might be hiding in existing telescope data, masquerading as distant galaxies or unexplained infrared glows. Yet the most tantalizing clue might lie in the early universe's chemical makeup. Dark stars would have polluted space with unique isotopes, leaving a fingerprint distinct from fusion-born elements. As telescopes like JWST peer deeper into cosmic history, they might spot pockets of primordial gas with compositions that only dark stars could explain. For now, these shadowy giants remain ghosts in the equations of cosmologists, but if confirmed, they'd prove the universe's first starlight didn't come from fire, but from something far more mysterious. In the ancient stellar cities known as globular clusters, where stars cram together by the millions, astronomers have stumbled upon a cosmic contradiction: stars that glow too blue, burn too bright, and behave far too youthfully for their surroundings. These celestial anomalies, called blue stragglers, should have burned out billions of years ago like their cluster siblings. Instead, they blaze with the vigor of stars half their age, flouting the rules of stellar evolution in plain sight. The secret to their rebellious energy likely lies in cosmic cannibalism. Picture two aging stars locked in a gravitational waltz, their orbits tightening over millennia until collision. In the crowded confines of a globular cluster where stars brush past one another at dizzying speeds, such mergers aren't just possible, they're inevitable. When two smaller stars fuse, their combined mass reignites nuclear fusion with a vengeance, creating a single, hotter, bluer star that masquerades as a youthful upstart. It's like tossing fresh logs onto a dying fire. The merger gives the reborn star a second life, complete with a fresh stock of hydrogen fuel and a surface temperature that betrays no hint of its violent origin. Hubble's sharp eyes have caught blue stragglers in the act. In the cluster M30, observations reveal stars with bizarre chemical compositions, their outer layers scrubbed of certain elements as if stirred by some unseen force. This matches precisely what models predict. When stars merge, their outer atmospheres mix violently, diluting traces of elements like carbon and oxygen that normally concentrate near a star's surface. Even more telling, some blue stragglers spin at breakneck speeds, a telltale sign of the angular momentum inherited from their progenitor star's death spiral. But mergers aren't the only explanation. Some blue stragglers might be stealing life rather than sharing it. In binary systems, a greedy star can siphon gas from its companion, bulking up until it crosses into blue straggler territory. Like a vampire growing stronger as its victim weakens, these stars rejuvenate themselves by draining their neighbors, a process written in the faint X-ray glow of leftover accretion disks. Yet the mystery deepens when we look beyond globular clusters. Open clusters and even the Milky Way's halo host their own blue stragglers, environments far too sparse for frequent collisions. Here, alternative theories emerge. Perhaps these stars were born unusually massive, their slow-burning cores defying expectations. Or maybe they've ingested rogue gas clouds, topping up their fuel reserves like interstellar gas stations. What's undeniable is that blue stragglers force us to rethink stardom's boundaries. They prove that in the universe's dense stellar metropolises, death isn't always the end. Sometimes it's just a prelude to a spectacular second act. And as telescopes probe deeper into these clusters, each blue straggler whispers the same tantalizing question: how many other cosmic resurrections are hiding in plain sight? When neutron stars collide, they don't just create a spectacular light show. They forge the very elements that make up our world in a cosmic alchemy far more extreme than anything happening inside massive stars. Picture two city-sized spheres of pure neutronium, each more massive than our Sun, spiraling toward each other at nearly light speed. Upon impact, they unleash a kilonova, an explosion so energetic it briefly outshines entire galaxies while spewing out neutron-rich material at velocities approaching 1/3 the speed of light. In those chaotic moments, something miraculous happens. The extreme conditions transform ordinary matter into gold, platinum, uranium, and other heavy elements through a rapid capture process known as the R process. While massive stars create lighter elements like carbon and oxygen through steady fusion, they often lack the neutron flux necessary to build heavier nuclei. Even in their explosive deaths as supernova, they typically only produce elements up to iron on the periodic table. But kilonovas, they're nature's ultimate particle accelerators, bombarding atomic nuclei with so many free neutrons that elements grow massive almost instantly. A single neutron star merger can eject up to 10 Earth masses worth of precious metals into space, enough to gild every planet in the Milky Way hundreds of times over. The evidence for this stellar smelting process arrived in 2017, when gravitational wave detectors caught the tremors from neutron star collision GW170817. Follow-up observations revealed telltale signatures of strontium and other R-process elements in the expanding debris cloud, confirming what theorists had long suspected. This cosmic gold rush happens on timescales that defy imagination. While massive stars take millennia to forge silicon or sulfur, kilonovas can create a platinum atom in less time than it takes for light to cross a single proton. Yet there's an intriguing paradox at play. Despite their phenomenal output, kilonovas are vanishingly rare, occurring perhaps once every 100,000 years per galaxy. Compare that to massive stars, which explode as supernova about once per century. This scarcity makes their contribution to the universe's heavy elements even more astonishing. Recent studies suggest nearly all the gold in your jewelry, the uranium in nuclear reactors, and the platinum in catalytic converters might trace their origins to these ultra-rare cosmic smash-ups rather than the more common stellar explosions. The implications stretch beyond mere chemistry. Because neutron star mergers distribute their heavy elements in narrow, high-velocity jets, they may explain why some ancient stars contain unexpected pockets of precious metals. These anomalies could be cosmic breadcrumbs marking where kilonova debris collided with primordial gas clouds billions of years ago. It also means the atoms in your wedding ring likely traveled across intergalactic space for eons before finding their way into Earth's crust, a journey far more epic than any mined gemstone could ever claim. As for the leftovers, the collision typically forms either an even more massive neutron star or collapses directly into a black hole, leaving behind an invisible monument to the most extravagant jewelry store the universe has ever known. So while massive stars dominate the cosmic spotlight, it's their dense, dead remnants that truly spin straw into gold, proving that sometimes the greatest treasures are born from catastrophe. Some stars don't just burn, they sing. Hidden among the cosmos are peculiar binary systems known as heartbeat stars, massive pairs locked in such an intense gravitational embrace that their very light pulses rhythmically like a cosmic electrocardiogram. These aren't the steady flickers of ordinary variable stars, they're erratic, dramatic surges and dips caused by tidal forces stretching and squeezing the stars with every orbital dance. When the Kepler Space Telescope first caught these patterns, astronomers were stunned. The data revealed light curves so precise they could set them to music, each peak and trough marking the moment these stellar giants reached their closest approach, their surfaces distorted into teardrop shapes by mutual gravitational pull. Take the system KP 12218663, for example. This pair, located roughly 3,000 light-years away in the constellation Lyra, orbit so closely that their mutual gravity distorts their outer layers into elongated ovals before relaxing back into spheres as they separate. The result, their combined brightness surges by nearly 20% during closest approach, and enough to be spotted across intergalactic distances. The Kepler data captured this rhythm with such clarity it revealed something even more astonishing. Tiny oscillations within the oscillations, subtle quivers in the star's surfaces caused by internal vibrations amplified by the tidal forces. It's as if the stars aren't just pulsing, they're humming, resonating like bells struck by their partner's gravity. What makes heartbeat stars truly extraordinary is how they expose the hidden fluidity of stellar surfaces. Most stars seem static from afar, but these binaries prove even massive celestial bodies behave like liquid when subjected to extreme forces. As the stars swing past each other, their atmospheres slosh back and forth, creating shockwaves that heat their surfaces unevenly. Some heartbeat stars even exhibit tidal earthquakes, sudden releases of pent-up energy that send ripples through their interiors, detectable as minute flickers in their light curves. Yet the most fascinating insight comes from their orbits. Unlike most binaries which settle into predictable paths, heartbeat stars often trace wild, eccentric routes around each other. Some take months to complete a single orbit, their dramatic separations and reunions playing out like a slow-motion cosmic tango. Others whip around each other in days, their mutual distortion so extreme they nearly touch before springing apart again. These chaotic dances aren't just beautiful, they're teaching astronomers how massive stars transfer energy and angular momentum, reshaping our understanding of stellar evolution in dense star clusters where close encounters are common. And here's the twist, these systems might be cosmic time capsules. Many heartbeat stars contain chemically peculiar compositions, their surfaces enriched with elements like strontium and barium, traces of past mass transfer between the pair. Some may have even stolen material from a third, now vanished companion, their rhythmic pulses echoing the drama of a long-ago stellar heist. As telescopes continue monitoring these celestial metronomes, each new observation peels back another layer, revealing a universe where even the mightiest stars move to rhythms deeper than we ever imagined. Astronomers call it the red supergiant problem, a cosmic mystery where the math just doesn't add up. Models predict the universe should be teeming with these swollen, aging giants, yet observations show a glaring shortage, as if half the stars expected to reach this late life stage simply vanished into thin air. Take Betelgeuse, the fiery shoulder of Orion. It's one of the few confirmed red supergiants we've studied closely, but statistically, there should be dozens more like it visible in our galactic neighborhood. So where did they all go? One compelling theory suggests these stars don't linger in their red supergiant phase as long as we thought. Instead of spending millions of years slowly puffing up, they might undergo violent internal upheavals that accelerate their demise. Betelgeuse's erratic behavior gives us clues. Its sudden dimming in 2019, caused by a colossal dust cloud ejected from its surface, hints at an unstable star shedding mass at an alarming rate. If other red supergiants are equally turbulent, they could be skipping the textbook retirement phase entirely, hurling off their outer layers prematurely and rushing toward supernova explosions far quicker than models predict. Another possibility, many red supergiants might collapse directly into black holes without the fanfare of a supernova. Normally, when a massive star exhausts its fuel, its core implodes, triggering a shockwave that blasts the outer layers into space in a dazzling explosion. But for stars at the upper mass range, simulations show the core might sometimes swallow the shockwave entirely, the star disappearing into a black hole with barely a whimper. No luminous fireworks, just a silent vanishing act. This failed supernova scenario would explain why we're missing so many red supergiants. They're not fading gently into old age, they're being erased. Then there's the dust factor. red supergiants are notorious for shrouding themselves in thick cocoons of ejected material, which could be obscuring them from our telescopes. Infrared observations have revealed hidden stars buried within these dusty veils, suggesting we might be overlooking an entire population simply because their light is too dim or red-shifted to detect with traditional methods. Even Betelgeuse, relatively close at just 640 light-years, surprises us with how much it hides. Its surface features remain blurry despite decades of study. The stakes are higher than just solving a head-count puzzle. Red supergiants are cosmic furnaces, forging elements like oxygen and carbon that seed future generations of stars and planets. If they're vanishing earlier or differently than we thought, it changes our understanding of how galaxies enrich themselves with the building blocks of life. And with Betelgeuse ticking toward its inevitable explosion, an event that could happen tomorrow or 100,000 years from now, we might soon get front-row seats to the death throes of one of these enigmatic giants. When it goes, the blast could outshine the full moon for weeks, leaving behind either a neutron star or a black hole as its tombstone. Either way, its final act could finally crack the mystery wide open, revealing what really happens when the universe's most massive stars reach the end of the line. Until then, the red supergiant problem remains a tantalizing reminder that even the brightest giants can disappear without a trace. The habitable zones around the universe's most massive stars aren't just larger than ours, they're practically another dimension of cosmic real estate. Picture Earth snugly orbiting the Sun at just the right distance for liquid water to exist. Now replace our modest star with a hypergiant like UY Scuti or Stephenson 218. Suddenly, the Goldilocks zone where temperatures could support life stretches so far out that a planet would need to orbit at Pluto-like distances just to avoid being vaporized. But here's the twist: even at these extreme ranges, the conditions would be nothing like our solar system's frozen outskirts. Take a planet circling a star like Eta Carinae. At a distance equivalent to Neptune's orbit, it would bask in perpetual daylight, drenched in ultraviolet radiation so intense it could strip atmospheres in centuries. Yet move it farther out, say, where Pluto orbits, and things get stranger still. The star's colossal luminosity would heat the planet's surface to temperatures rivaling Earth's, but with a catch: the sunlight would arrive as a searing, concentrated beam rather than the diffuse glow we know. Days would be blindingly bright, while nights, if the planet even had a day-night cycle, might never truly grow dark, thanks to the star's lingering glow across billions of kilometers. And then there's time. Massive stars burn so fiercely that their habitable zones are fleeting. A planet orbiting in the right spot might enjoy stable conditions for only a few million years, a heartbeat compared to Earth's 4.5 billion years of relative calm. By the time life could even begin to emerge, the star might already be shedding its outer layers or preparing for a cataclysmic supernova, sterilizing any hopeful biospheres in an instant. What's truly mind-bending is the scale of these systems. A planet orbiting a hypergiant at Pluto-like distances would take not 250 years to complete a single orbit, but tens of thousands. Seasons, if they existed at all, would last millennia. Tidal forces from the star's gravity could lock the planet's rotation, leaving one side perpetually scorched and the other frozen in eternal shadow. And yet, despite these extremes, the sheer size of these stars means their habitable zones are vast enough to contain entire planetary systems within them, like nesting dolls of potential worlds. The irony: while these zones are staggeringly large, they're also eerily empty. Stars this massive are rare, and their violent stellar winds carve out so much space around them that forming planets in their vicinity is nearly impossible. Any worlds that did manage to coalesce would likely be gas giants or barren rocks, their surfaces scoured clean by radiation long before life could take hold. Still, the thought experiment is irresistible. Somewhere in the universe there might exist a planet where the sun fills half the sky. its habitable zone a fragile, transient ribbon in an ocean of fire and ice. And if life did arise there, even briefly, its view of the cosmos would be unlike anything we can fathom. A sky dominated by a star so vast it makes our sun look like a distant matchstick flame. Some stars don't just drift through the galaxy, they flee like cosmic fugitives, hurled into the void at speeds that defy logic. These hypervelocity stars, the universe's ultimate runaways, tear through space at millions of miles per hour, their trajectories tracing violent paths we're only beginning to unravel. Take HD 271791, a massive blue star racing outward at 2.2 million miles per hour, fast enough to cross the continental United States in less than 2 seconds. At that speed, it's not just leaving its birthplace behind, it's escaping the Milky Way entirely, destined to vanish into the intergalactic darkness. So how does a star reach such impossible velocities? The culprits are some of the most destructive forces in the cosmos. One scenario involves a supernova in a tight binary system. When one star explodes, the sudden release of its gravitational grip can slingshot its companion outward like a celestial catapult. Imagine standing on a merry-go-round that suddenly disintegrates beneath you, flinging you into open space. That's the fate of these stars, their momentum carrying them far beyond their galactic neighborhoods. But supernovae aren't the only trigger. Lurking at the heart of our galaxy, the supermassive black hole Sagittarius, a star, plays a far more sinister role. When binary star systems wander too close, the black hole's immense gravity can rip them apart, capturing one star while violently ejecting the other. It's a cosmic game of gravitational pinball, where the survivor gets hurled away at speeds approaching 3 million miles per hour. These ejections aren't just fast, they're precise, with trajectories so straight they could be drawn by a ruler across the night sky. The real marvel is how we've learned to track these stellar fugitives. By analyzing their light, astronomers can trace their paths backward, like rewinding a film reel to uncover their origins. HD 271791, for example, appears to have been launched from the outer edges of the Milky Way's disk, not the galactic center, hinting at an alternative ejection method, possibly involving a rogue intermediate mass black hole. Other hypervelocity stars, like the infamous S5 HVS1, point directly back to Sagittarius, a star, their paths serving as cosmic breadcrumbs leading to the scene of the crime. Yet the implications stretch beyond mere celestial mechanics. These runaway stars carry with them the chemical fingerprints of their birthplaces, offering clues about distant regions of the galaxy we've never directly observed. Some may even transport planets along for the ride, worlds torn from their original orbits and sent careening through intergalactic space, their skies growing darker as their parent star leaves the Milky Way's glow behind. And then there's the ultimate irony. Many hypervelocity stars are massive and short-lived, destined to explode as supernova far from any galaxy, their final eruptions lighting up the cosmic voids like solitary fireworks in an endless night. For now, they streak through the darkness, silent witnesses to the violence that shaped them, and reminders that even in the seeming order of the cosmos, chaos always has the last word. Alpha Centauri, the closest star system to our Sun, hides a cosmic paradox in plain sight. While its brightest member, Alpha Centauri A, appears as a single point of light to the naked eye, telescopes reveal a gravitational ballet of 3 stars, 2 Sun-like stars locked in a tight orbit, with a third, far smaller companion circling them from an astonishing distance. This triple arrangement isn't just rare, it defies conventional wisdom about how massive stars can coexist without tearing each other apart. The secret lies in an intricate orbital hierarchy that keeps this stellar family from collapsing into chaos. Take the primary pair, Alpha Centauri A and B. These 2 stars whirl around each other every 80 years, their separation varying from roughly the distance of Saturn to the Sun down to a mere 11 astronomical units closer than Saturn orbits our star. At such close quarters, their mutual gravity creates a dynamic playground of tidal forces, each star subtly distorting the other's shape with every pass. Yet they persist, locked in a stable dance thanks to their nearly circular orbits and balanced masses. Now introduce Proxima Centauri, the system's third member, a red dwarf so distant it takes over 500,000 years to complete a single loop around the duo. This extreme separation acts as a cosmic shock absorber, preventing Proxima's feeble gravity from destabilizing the inner pair. The real marvel is how such configurations even form. Most multiple star systems originate from fragmented molecular clouds, but maintaining stability with 3 or more massive components requires near-perfect initial conditions. Too much turbulence during birth, and the stars either merge or fling each other into interstellar space. Alpha Centauri's delicate equilibrium suggests it emerged from an unusually orderly collapse, its stars settling into orbits precise enough to last billions of years. Even so, the system isn't perfectly static. Simulations show subtle gravitational nudges from passing stars or interstellar clouds could, over eons, alter Proxima's trajectory enough to destabilize the entire arrangement. What's truly fascinating are the hypothetical orbits of any planets in this system. A world orbiting Alpha Centauri would face dramatic shifts in its night sky periods where its second sun appears as a brilliant star, followed by decades where it shrinks to a mere pinprick. Meanwhile, Proxima's feeble glow would barely register, flickering like a distant campfire against the backdrop of the inner pair's radiance. And if a planet somehow orbited all 3 stars, its path would be a chaotic roller coaster, subjected to gravitational tugs from multiple directions that could heat its core through tidal friction alone. Yet Alpha Centauri isn't alone in its complexity. Far across the galaxy, systems like Polaris, the North Star, harbor even more exotic arrangements. Polaris isn't just a triple but a triple of triples, with each component itself part of a tighter binary or trinary subsystem. These nested hierarchies push the limits of gravitational physics, their stability maintained by precise ratios of mass and distance that border on mathematical art. Some theorists suggest such systems might be cosmic factories for hypervelocity stars. When one member gets ejected, the remaining stars recoil with enough energy to send them careening across the galaxy. The takeaway: triple star systems are nature's tightrope acts, balancing on the edge between order and chaos. They prove that even in a universe ruled by gravity's unrelenting pull, there's room for delicate, lasting harmony as long as the stars agree to dance to the same rhythm. And for astronomers, each newly discovered trio offers fresh clues about how the most massive stars negotiate their crowded celestial neighborhoods without collapsing into catastrophe. In the cosmic tapestry of star formation, there's nothing quite like a starburst galaxy, an entire region of space gripped by a feverish, galaxy-wide birthing frenzy of new stars. At the heart of these celestial fireworks displays are the universe's most massive stars, their explosive births and deaths driving a cycle of creation so intense it can reshape entire galaxies. Take M82, the Cigar Galaxy, a chaotic whirlwind of dust and fire where stars are being born at a rate 10 times faster than in our Milky Way. Peer into its core in infrared light, and the scene is nothing short of apocalyptic. Vast clouds of gas and dust glow neon pink as they're shredded by the intense radiation of countless newborn hypergiants, their fierce ultraviolet light carving out bubbles and pillars like a cosmic sculptor wielding a blowtorch. What triggers these runaway stellar nurseries? The answer often lies in galactic collisions or near misses. When galaxies brush past each other, their gravitational interplay sends shockwaves through their interstellar gas, compressing it into dense knots where stars form in rapid succession. But here's where massive stars take center stage. They don't just emerge from this chaos, they amplify it. Each new hypergiant floods its surroundings with radiation and stellar winds, heating nearby gas clouds and triggering further collapses in a domino effect of star formation. It's a self-perpetuating cycle. The more massive stars that form, the more they churn up the environment to birth even more stars. In M82, this process has become so extreme that the galaxy's core is essentially one gigantic stellar maternity ward, with clusters of young, massive stars packing together so tightly their combined glow outshines the rest of the galaxy. Yet these starburst regions aren't just about creation, they're also monuments to destruction. The same massive stars that light up these nurseries also die young, exploding as supernova at a rate far higher than in quieter galaxies like our own. Each detonation sends shockwaves rippling through the surrounding gas, seeding it with heavy elements while simultaneously compressing it to birth the next generation. Hubble's sharp vision has caught these processes mid-action. In one breathtaking image of M82, delicate filaments of oxygen-rich gas stretch for thousands of light years. The spectral graves of countless hypergiants that lived fast, died young, and fertilized the cosmos with the raw materials for planets and life. The true scale of this frenzy becomes clear when we compare starburst galaxies to our own sleepy Milky Way. Where our galaxy might form 1 or 2 new stars per year on average, a starburst galaxy like M82 can produce dozens, sometimes hundreds in the same time frame. And most of those are massive stars, the kind that burn bright and vanish in a few million years. This intensity can't last forever, of course. Eventually, the galaxy will exhaust its gas reserves, the stellar birth rate will plummet, and the frenzy will fade into a quieter middle age. But for now, starburst galaxies stand as the universe's most spectacular laboratories, places where the rules of star formation are pushed to their limits, and where massive stars don't just inhabit the cosmos, they actively reshape it with every fiery breath. Every second, trillions of invisible bullets tear through your body, cosmic rays, subatomic particles hurled across space with energies that dwarf anything human-made accelerators can produce. These aren't random space debris, they're the fingerprints of dying massive stars, particles accelerated to over 99% the speed of light by some of the most violent events in the cosmos. When a hypergiant star reaches its final moments, its collapsing core doesn't just explode outward, it becomes nature's ultimate particle cannon, launching protons and atomic nuclei across interstellar space with unfathomable force. The process begins in the supernova's shockwave, an expanding wall of plasma denser than lead and hotter than the sun's core. As this wave plows through the star's outer layers, it encounters twisted magnetic fields trillions of times stronger than Earth. These fields act like cosmic slingshots, trapping charged particles and whipping them back and forth across the shock front, with each pass adding more energy. Picture a pinball ricocheting between bumpers at ever-increasing speeds, except here, the pinball is a proton reaching velocities so extreme it could circle our planet 7 times in 1 second. But the real magic happens when these particles escape. Some cosmic rays generated by supernova travel for millions of years before reaching Earth, their paths bent into spirals by the galaxy's magnetic fields. When they finally strike our atmosphere, they trigger cascades of secondary particles called air showers. One initial cosmic ray can produce billions of daughter particles raining down over several square kilometers. These events are so energetic that scientists have detected some with the kinetic equivalent of a fast-pitched baseball, all packed into a single subatomic particle. What's astonishing is how much these stellar artifacts affect our world. Cosmic rays from massive stars constantly seed Earth's atmosphere with particles that may influence cloud formation, and some theories even suggest they could play a role in triggering lightning strikes. They also pose challenges for future astronauts. A single high-energy cosmic ray passing through a spacecraft could scramble electronics or damage human DNA like a microscopic shotgun blast. Yet these same particles have given us clues about distant supernovae. When astronomers trace back the paths of particularly energetic cosmic rays, they often point toward known stellar remnants like the Vela supernova. its shockwaves still accelerating particles 11,000 years after the explosion. The most extreme cosmic rays, however, come from beyond our galaxy. Dubbed "Oh my God" particles, these rare projectiles carry energies millions of times greater than anything the Large Hadron Collider can produce. While their exact origins remain mysterious, many astrophysicists suspect their link to hypernova or active galactic nuclei cosmic engines powered by supermassive black holes feasting on stellar debris. Whatever their source, one thing is clear: when massive stars die, they don't fade quietly into the night. They bombard the universe with subatomic shrapnel, their final acts echoing across space and time in the form of invisible, ultra-relativistic bullets that have been striking Earth since long before life began, and will continue long after we're gone. The idea of massive stars leaving behind diamond-studded corpses sounds like something from a cosmic fairy tale, but the truth is far stranger than fiction. While headlines often claim that white dwarfs contain diamonds the size of planets, the reality of these stellar remnants is both more fascinating and less sparkly than the myths suggest. The confusion starts with the fate of carbon-rich massive stars. After exhausting their nuclear fuel, stars like our Sun will shed their outer layers and collapse into white dwarfs, incredibly dense objects where a teaspoon of material can weigh as much as an elephant. For stars with just the right mass, these cores consist mostly of crystallized carbon, a structure that shares some properties with diamonds but behaves in ways gemstones never could. First, let's clear up the biggest misconception. These diamonds aren't glittering, faceted gems floating in space. The carbon inside a white dwarf forms a crystal lattice due to extreme pressure, similar to how diamonds form deep in Earth's mantle, but the conditions are so extreme that the material becomes an exotic quantum matter state unlike anything found on Earth. Imagine a substance so dense that electrons are nearly immobilized, creating a conductive metal-like core rather than the transparent gem we associate with jewelry. The carbon here isn't neatly arranged into perfect crystals either. It's a chaotic, ultra-compressed sea of nuclei forced into a rigid structure by pressures 1,000,000 times greater than Earth's atmosphere. Then there's the issue of time. A white dwarf's crystallization process takes billions of years, far longer than the current age of the universe for many of these objects. While models predict that some of the oldest white dwarfs, like BPM 37093, nicknamed Lucy after the Beatles' song, may have begun crystallizing, they're not single planet-sized gems. Instead, their interiors likely resemble a vast, slowly hardening sludge where pockets of crystallized carbon mix with oxygen and other elements, more like a cosmic ice sheet freezing in slow motion than a pristine diamond. Even more intriguing is what happens to these diamond cores over deep time. As white dwarfs cool, their crystallization releases latent heat, temporarily slowing their fading glow. This process can cause pulsations, subtle brightness variations that let astronomers probe their interiors like seismic waves revealing Earth's layers. Some crystallizing white dwarfs even exhibit strange magnetic fields, suggesting their solidifying cores generate currents strong enough to warp the star's entire magnetic architecture. So while it's tempting to picture a lone diamond drifting through the void, the real story is far richer. These stellar remnants are cosmic alchemy labs where matter is compressed and rearranged into states that defy ordinary physics. They might not be literal gems, but their true nature, part crystal, part quantum oddity, makes them infinitely more interesting than any spacefaring jewel could ever be. The universe doesn't need literal diamonds to be wondrous. It crafts marvels beyond our imagination from the simplest of elements. Massive stars aren't just inhabitants of galaxies, they're the architects that build them from the inside out. When these titans reach the end of their brief, fiery lives, their explosive deaths become cosmic construction sites, scattering enriched material across interstellar space like celestial confetti. A single supernova can distribute elements equivalent to 50 solar masses: oxygen, carbon, iron, and even heavier atoms like gold and uranium throughout its galactic neighborhood. This isn't just stellar debris, it's the raw material for everything from rocky planets to complex organic molecules. Consider the Crab Nebula, the glowing wreckage of a supernova witnessed by Chinese astronomers in 1054. Modern telescopes reveal a chaotic web of filaments rich in oxygen, sulfur, and neon elements forged during the star's final moments and now being recycled into new generations of stars. The expanding shockwave from that ancient explosion is still plowing through surrounding gas clouds 1100 years later, compressing them into dense knots where gravity will eventually birth new stellar systems. This cycle of destruction and rebirth explains why later generation stars like our Sun contain traces of heavy elements. We're literally made from the ashes of long-dead giants. The process works on astonishing scales. In star-forming regions like the Orion Nebula, astronomers have detected superbubbles, vast cavities hundreds of light years across carved by successive supernovae. These expanding shells of hot gas sweep up surrounding material like cosmic snowplows, creating dense ridges where gravitational collapse becomes inevitable. The most massive stars often form in clusters, meaning their deaths come in rapid succession, each explosion triggering waves of star formation that ripple through galactic arms. It's a self-perpetuating cycle. The more massive stars that form, the more supernovae occur, which in turn creates more stellar nurseries. But the influence doesn't stop at new stars. The heavy elements ejected by these supernovae fundamentally change a galaxy's chemical composition over time. Early in cosmic history, galaxies consisted mostly of hydrogen and helium, elements too light to form terrestrial planets. Only after generations of massive stars lived and died could rocky worlds like Earth emerge. The iron in our blood, the calcium in our bones, even the silicon in computer chips, all were once fused in the hearts of massive stars and scattered across the cosmos by their explosive deaths. The most stunning evidence comes from galactic archaeology. By analyzing the chemical fingerprints of ancient stars in the Milky Way's halo, astronomers have reconstructed our galaxy's violent youth, a time when supernova occurred hundreds of times more frequently than today. These primordial explosions didn't just enrich the interstellar medium, they helped shape the galaxy's very structure, their shockwaves carving out the vast spiral arms we see today. Modern computer simulations show that without this stellar feedback, the combined effect of supernova and stellar winds galaxies would collapse into featureless blobs, devoid of the intricate patterns that make them cosmic works of art. So when we gaze at the Milky Way's shimmering disk, we're not just seeing stars, we're witnessing the legacy of countless massive stars that lived fast, died young, and built the galactic landscape we call home. Their explosive final acts weren't endings, but vital chapters in an ongoing story of cosmic construction, one where every atom in our bodies was once part of something truly stellar. Astronomers have a problem. The math says the universe should be brimming with massive stars, hypergiants, luminous blue variables, Wolf-Rayets, yet our telescopes keep coming up short. It's not just a minor accounting error. Current observations suggest we're missing up to 2/3 of these cosmic behemoths, creating a glaring rift between theory and reality. This observed vs. theoretical gap forces us to confront an uncomfortable truth. Either our models of star formation are fundamentally flawed, or the universe is hiding its giants in plain sight. One leading suspect, cosmic dust, the same interstellar soot that paints the Milky Way's dark lanes in telescope images. Hypergiants and other massive stars are prolific dust factories, spewing out silicate and carbon grains that shroud them in opaque cocoons. Infrared observations reveal the scale of this camouflage. Stars like NML Cygni, visible only in specific wavelengths, are actually among the most luminous objects in the galaxy once you peer through their self-made veils. The dust doesn't just dim their light, it redistributes it, converting blistering ultraviolet radiation into longer infrared waves that slip past conventional optical telescopes unnoticed. But dust isn't the only cosmic magician at work. Detection limits play a sneaky role too. Even our most advanced instruments struggle to spot massive stars in distant galaxies where their light blends into the glow of surrounding stellar neighborhoods. Take the case of the Tarantula Nebula in the Large Magellanic Cloud, a mere 170,000 light-years away. When the James Webb Space Telescope turned its infrared gaze toward this stellar nursery, it uncovered previously hidden massive stars whose visible light was completely swallowed by intervening gas clouds. Extrapolate that challenge to galaxies millions of light-years distant, and the scale of our observational blind spot becomes staggering. Then there's the time factor working against us. Massive stars live fast and die young, their fleeting existence making them statistical needles in the galactic haystack. While a star like our Sun will shine for 10 billion years, a 200 solar mass hypergiant might last only 2 million, a cosmic blink during which it must be both actively forming and luminous enough for us to spot. Compounding the issue, these stars often form in dense, dusty clusters where younger siblings obscure our view. It's like trying to count fireflies in a thunderstorm. Just as you focus on one, another flares up nearby, distorting your tally. The implications ripple across astrophysics. If we're underestimating the number of massive stars, we might also be miscalculating how much heavy element enrichment they provide to galaxies: oxygen for water, carbon for life, iron for planetary cores. Supernova rates, stellar wind contributions, even black hole formation models all hinge on accurate counts of these stellar titans. Some theorists suggest radical solutions. Perhaps stars form differently in extreme environments, skipping the hypergiant phase entirely. Others propose that our galaxy harbors an unseen population of dark, massive stars, enshrouded so thoroughly they emit almost no detectable light at all. New technologies offer hope in closing this gap. Spectroscopic surveys like SDSSV are mapping millions of stars across multiple wavelengths, while radio telescopes like ALMA pierce dust clouds to reveal hidden stellar nurseries. Time-domain astronomy, tracking how stellar brightness changes over years, helps identify unstable massive stars by their telltale flickers, and gravitational wave detectors might one day sense the mergers of massive binaries we can't see optically. The mystery persists because massive stars refuse to follow neat theoretical boxes. Each discovery, whether a dust-cloaked Leviathan in Orion or a rogue hypergiant speeding through intergalactic space, adds complexity to the puzzle. Far from discouraging scientists, this gap between prediction and observation fuels their curiosity, proving that even in an age of advanced telescopes, the universe still keeps its most spectacular secrets tucked just out of sight. From hypergiants that could swallow our solar system whole to stellar vampires stealing their companions' lifeblood, these 30 facts reveal a universe far stranger and more spectacular than we ever imagined. These cosmic titans aren't just distant points of light. They're the architects of existence itself, forging the heavy elements in our bones, the oxygen in our lungs, and the carbon in our cells through their violent lives and explosive deaths. Whether it's UY Scuti's mind-bending scale, R136A1's rule-breaking mass, or the Pistol Star's hurricane-like winds, each of these stellar extremes pushes the boundaries of what we thought possible, rewriting the laws of physics with their sheer cosmic audacity. Their influence stretches far beyond their brief, brilliant lives. The shockwaves from their supernova carve out stellar nurseries, their gamma-ray bursts light up the universe, and their gravitational dances send hypervelocity stars streaking across the galaxy. Even in death, they shape the cosmos, collapsing into black holes that warp spacetime, leaving behind diamond-like white dwarfs, or vanishing entirely in pair instability, explosions so violent they leave no trace. The gold in your jewelry, the iron in your blood, even the screen you're watching right now, all were forged in these celestial crucibles billions of years ago, scattered across space by dying giants you'll never see. Yet for all we've discovered, the universe always holds deeper mysteries. What undiscovered behemoths lurk in dust-shrouded galactic cores? Could quark stars or dark matter giants exist beyond our current imagination? Every time we build a better telescope, we find stars that make our previous record breakers look ordinary. So who knows what cosmic leviathans still hide in the darkness? If this journey through stellar extremes left you awestruck, just wait, the universe has barely begun to reveal its wonders. For more mind-expanding space mysteries, don't forget to like and subscribe. The cosmos is vast, unpredictable, and full of stories waiting to be told. Hit that notification bell so you never miss our next adventure across the stars. After all, the universe doesn't keep secrets forever, and neither should we.